You can take over the session.
All right, so you see my screen again. Is it clear?
Yes, yes, sir. It's clear now.
Okay. First, I would like to thank the organizer. Uh, Organizing a conference during these hard days is not an easy task. We are all online. So I really thank you very much for organizing such conference, and thank you for inviting me. And I would like to add, I am a very regular customer to India. I used to visit India, like 4, 5, 6 times a year. So thank you very much. Okay, the talk uh, will be over rings which have prime ideals that are linearly ordered. Okay, this is kind of, like it gives you like simple condition to check whether the prime ideals are linearly ordered or not. Uh, okay, let's start the talk. So the first, here's the definition. Like you let R to be a commutative ring with 1 not equal 0, meaning commutative ring with identity. And what does it mean for the prime ideals are linearly ordered? If and only if, whenever you have two prime ideals of R, then you have Q1 is a subset of Q2, or Q2 is a subset of Q1. So that's the definition of linearly ordered. Whenever you have two prime ideals, then one of them has to be a subset of the other. And this is like, I just remind you with the radical of an ideal. If I is a proper ideal, then the radical of I will be the elements in R, where R to the n is in I for some positive integer n bigger or equal to 1. Okay? So if you want to follow my talk, you need to know the definition of linearly ordered. And of course, these are radical ideal. All of us know, you study it, maybe undergraduate. Okay. Here are the conditions. So the following statement are equivalent for a commutative ring R with identity. It's a complete description, and these statements are equivalent. So the prime ideals of R linearly ordered, it's the same as if you say the radical ideals of R are linearly ordered. And is the same if you say that each proper radical ideal of R is prime. So if the radical of each proper ideal is prime, then definitely the prime ideals will be linearly ordered. It's enough to say the radical ideal of principal ideals. The radical ideals of principal ideals are linearly ordered. For me, 5 is my favorite condition, because here give me like some divisibility condition to check. Whenever you have two elements in R, there should be an integer n, where A is a factor of B to the n, or B is a factor of A to the n. And n here definitely rely on A and B, not the same for all. So whenever you have A and B, we should be able to find an N that rely on A and B, where A is a factor of B to the N or B is a factor of A to the N. So these conditions, so it seems that this is a complete answer to the problem I just mentioned. When the prime ideals are linearly ordered. Okay, so let me remind you what we mean with an integral domain R. What do I mean with integral domain? Well, this is a reminder. It means a commutative ring with identity such that whenever you have the product of two elements is equal 0, then one of them has to be 0. It just like in the normal, whatever normal mean. Anyway, I will not mention normal. So integral domain is nothing but commutative ring with identity. And whenever you multiply two elements and you get 0, then one of them has to be 0. This integral domain, we call it greatest GCD domain. If the GCD exists for every A comma B in R. If the GCD exists, because we know there are some integral domain where the GCD does not exist. But I want the GCD exists for every A and B, the greatest common divisor, GCD. And also this is a reminder, what do we mean with valuation domain? There are many definitions of valuation domain. The one I use here is the simple one. Whenever you have two elements in R, then A has to be a factor of B, or B is a factor of A. Whenever you have A and B in R, then A is a factor of B, or B is a factor of A. That's the definition of a valuation domain. Okay, here is a result. If you have a GCD domain and the prime ideals are linearly ordered, then it has to be a valuation domain. So for a sufficient condition for a GCD domain to be a valuation domain, the prime ideals to be linearly ordered. Of course, they are, this is talk general. There are some, we can construct some fancy domain where the prime ideals are linearly ordered and your domain is not a valuation domain. So this is not true in general. What is not true in general? That if the prime ideals are linearly ordered, then it has to be a valuation domain. This need not to be true. But if I add a GCD domain and the prime ideals are linearly ordered, then I must have a valuation domain. And of course, the converse, if you have a valuation domain, then definitely the prime ideals are linearly ordered. And and it is a GCD domain, because if you have a valuation domain, by definition, whenever you have two elements, A and B, then A has to be a factor of B, or B has to be a factor of A. Okay, so here is another reminder. Maybe some of you seen this. What do we mean with divided prime? A prime ideal of a commutative ring we call it divided if Q is a subset of the ideal generated by R for every R outside Q. That's divided. Divided prime, first, this class of prime ideal is studied by David E. Dobbs. Maybe some of you hear the name. And then later on, I study it for rings in general. David E. Dobbs, he did it for integral domain. I did it for rings, commutative rings in general. So this is the concept of divided prime here. Well, if you have every prime ideal is divided, then your ring, we call it divided ring. So you know the definition of divided ring. Divided ring means every prime ideal is divided. Okay? All right. Okay, so here is an observation. If you have a divided ring, what does that mean? Every prime ideal is divided. Then definitely it's very easy to see that the prime ideals of divided rings are linearly ordered. I mean, this is just by definition, it follows. If you have a divided ring, then the prime ideals are linearly ordered. Okay, here is a theorem that gives me a complete characterization of divided ring. So R is a divided ring. It means for every proper ideal, IK of R, I is a subset of the radical of K, or the radical of K is a subset of I. Whenever you have two proper ideals, then one of these statements must hold. I is a subset of the radical of K, or the radical of K is a subset of I. Okay. Number 3, for every A and B we have, I mean, here I'm choosing element. So I'm taking a principal ideal of AR has to be in the radical, or the radical has to be in AR. Okay? One of them has to be. And number 4, and I'm not sure if I wrote number 4 correctly. Let me go back to the previous. Oh no, this is not the previous. Uh, yeah, okay, I'm fine with that. Yes, this is okay. Number 5. I thought I repeated number 5 here, but that is not the case. Okay. So number 4, for every A and B, either A is a factor of B or B is a factor of a to the n for some integer n bigger or equal to 1. Usually, I like these conditions. I like to think of one, 1 and 4. Why do I like that? Seems like I'm giving some connection between rings and number theory in a way for me, using the language of factoring and so on. Uh, this condition here is equivalent for the ring to be divided ring. Okay. Uh, and of course, if you look at number 4 and the definition of valuation domain, the definition of valuation domain, that whenever you have two elements, A and B, then A has to be a factor of B, or B has to be a factor of A. So definitely for any valuation domain, number 4 hold. So quickly, you know that R is a divided ring. It's already known, valuation domain are divided rings. And let me stop for a minute here and tell you something. Maybe you're gonna ask the question, if you have a divided domain, like your ring is integral domain and is divided, does it mean a valuation domain? The answer is no. In fact, there are many classes of rings that are not a valuation domain, but at the same time, they are divided rings. So if you have this question in mind, the answer is no. If so, it goes only one direction. If you have a valuation domain, then the ring is divided, but divided never imply a valuation domain. It's only one direction. Okay, then you start doing the natural things. What about the homomorphic image of a divided ring? That's a good question. Like if you have a ring homomorphism from A to B and A is divided, what do we know about the image of A? So it's divided. The answer is divided. Any homomorphic image of a divided ring is divided. In particular, if R is a divided ring and I is a proper ideal, then R mod I is a divided ring. And then you're gonna ask another question, what about localization? Like if you select a multiplicatively closed subset S, and you localize R at this set, then also divided if the ring is divided. So any localization of a divided ring is divided. The homomorphic image of a divided ring is divided, and localization is divided. Okay? All right. If you look at the next result, kind of interesting in a way. Here I'm taking, let n be the set of all non-unit element of a commutative ring. So remember, n even does not need to be an ideal. I'm only taking this, except if your ring has exactly one maximal ideal. If your ring has exactly one maximal ideal, then definitely n will be this maximal ideal. But the hypothesis, we only taking n to be the set of all non-unit element of a commutative ring. Then here is a divisibility condition, how you check if the ring is divided. R is the divided ring. This is equivalent that whenever you have two elements in R, we should be able to come up with an integer n bigger or equal to 1, where AR, the ideal generated by A, is a subset of Bn, b to the n times n. Okay? Or, hello, can you hear me? Can you still hear me?
Yes, Professor. We
Okay,
can
thank
hear
you.
you.
All
Thank you.
right, thank you. Or b to the n, n is a subset of AR. So here are other conditions how to check if the ring is divided or not. Okay, this is also recall. We know the definition of a primary ideal. Primary ideal means whenever you have two elements, A and B, and the product is in I, then A has to be in I or B has to be in the radical of I. Of course, from the definition missing, I should say a proper ideal is primary if whenever A, B in I for some A, comma B in R. Whenever you have two elements in R and the product is in I, then A has to be in I or B has to be in the radical of I. And also we recall what we mean with the zero divisor element of a ring. If R is a commutative ring, then the zero divisor element are the elements in R where AB equals 0 for some non-zero element B in R. Okay, so the zeros of a ring are the elements in R, A in R, where AB equals 0 for some non-zero element B in R. Okay, and here is an observation. In fact, you know, I think most of you, if not all of you, know how to construct what I have written here. If a Q is a prime ideal and you have n bigger or equal to 2, then Q to the n need not be primary. Okay? If you have a prime ideal, that was like, you know, one of the question in the, I don't know, old days. Does it mean if you take Q to the n, will it be a primary ideal? In general, this need not to be true. Also observe that if I is a primary, then the radical of I has to be prime. Okay? Why this question? You see why? Because the radical of a Qn, if a Q is a prime, and you take the ideal Q to the power n, then the radical of this ideal Q to the n will be Q. So the question was, will it be primary or not? As I mentioned, this need not to be true in general. However, here is the result. What about if I add divided prime? not just a prime. A Q is a divided prime, and this is crucial. The zero divisor element of R, ZR is here. I give it in the definition. I mean, most of you know it, just in case. And the zero divisor element of R, subset of a Q, then a Q to the N is a primary for every integer. So here I need to add two conditions, divided and this condition, the zero divisor element of R in a Q. Okay, the question here, you see what I'm using here? I'm using proper. I'm not saying the zero divisor proper or equal Q. In fact, I constructed an example where this condition, what condition? The zero divisor element, it has to be proper subset of a Q. If equal, then this result may not be true. So it was like very crucial condition for proper here, not subset or equal. So that this is not a typo. We meant that. Okay, so here is a condition where this result will be true if you have a prime ideal Q. When will be Q to the N primary? One answer if Q is divided with this condition. Okay, all right. What is the definition of atomic domain? Atomic domain, it means every non-unit element is a product of irreducible element. And here we have to be careful. I'm not saying it has to be unique factorization domain, because we know in unique factorization domain, every element is a product of irreducible element. But remember, in unique factorization domain, then you can factor each element, or you can write each element a product of irreducible element uniquely up to associative. You know, I mean, this is something you studied in. So definitely unique factorization domain are atomic, but not every atomic is unique factorization domain. I mean, or maybe some of you study half factorial domain, and there is a famous integral domain that is not unique factorization domain. I think it's Z, and you add the radical of -5 to it, if I recall correctly. Anyway, there are many integral domains that are not unique factorization domain, but they are atomic. Okay, so here's a result. If you have an atomic domain that is not a field, then R is a divided domain if and only if R has exactly one maximal ideal, call it M, and there is no other prime ideals between 0 and M. You see, if R has exactly one maximal ideal, M, and 0, M are the only prime ideals. Well, another way to say that, if and only if R has exactly one maximal ideal, and the Kroll dimension is 1. But I avoid to divide, I mean, in general talk, to give you what we mean with the Kroll dimension. So I mention exactly what the Kroll dimension means here. Kroll dimension 1 means there is no proper ideal, no proper prime ideal between 0 and m. The only prime ideals are 0 and m. So here is a complete characterization when an atomic domain will be divided domain. Okay, this is kind of interesting, this result here. And this, I finish my talk early, so you can have lunch break. Number, the last one, yeah. What does it say? It says that if you have an integral domain, then the following, okay, let me see, I have missed. Yeah, this one here. This has to do with finitely generated prime ideal. Because, of course, all of us know finitely generated prime ideal need not be maximal. I mean, all of us know that. Finitely generated prime ideal, they do not need to be maximum. So let R be a commutative ring with identity, and I have a Q to be divided finitely generated prime ideal. So what did I add? I add divided. I have finitely generated prime ideal and divided. And also with one more condition, assume there is an S in a Q for some S in R, but not in the set of the 0 element of R. So your S here, assume there is an S in a Q. This S is not a 0 element of R. Then the conclusion, a Q has to be is the only maximal ideal of R. So if you have finitely generated divided, then and with this condition, then definitely this ideal will be maximal ideal. Okay. Here is another, I will end up my talk with this. There's Avenue Houston and Hedstrom. They introduced a class of integral domain. They call them the pseudo-valuation domain. And what is the definition of a pseudo-valuation domain? First, you want to know what we mean with the strongly prime. We know the definition of a prime ideal. What do we mean with a strongly prime ideal? A prime ideal Q of R, we call it strongly prime if whenever xy in a Q for some xy in K. What is K? K is the quotient field of R. Here from the beginning, R is integral domain with a quotient field K. And you take a prime ideal of R. Then we call it a strongly prime if whenever xy in a Q for some xy in K, then X has to be in a Q or Y in a Q. If every prime ideal is a strongly prime, then we call the ring pseudo-valuation domain. Okay? Here is the divisibility condition. By the way, every valuation domain is a pseudo-valuation domain. But not every pseudo-valuation is a valuation. So the valuation domain live inside the class of pseudo-valuation domain. Here is a characterization of pseudo-valuation domain. Let R be an integral domain. The following are equivalent. R is a pseudo-valuation domain. This is the same as if you say for every A, B in R, A is a factor of B, or B is a factor of AC for every non-unit C in R. So again, these symbol condition, I always enjoy to give divisibility condition to classify certain classes of integral domain. Just like the classification of valuation domain. I mean, there are so many fancy classification, but the simplest one, whenever you have two elements, then one of them has to be a factor of the other. The same thing here. There are many classification of pseudo-valuation domain, but here is a simple divisibility condition that whenever you have two elements, then A is a factor of B, or B has to be a factor of AC for every non-unit C in R. I think that's enough for me, and I thank you for inviting me and for listening, and thank the organizer again for the hard work, and I stop here. Thank you.
Thank you, sir. Dear audience, if you have any questions, you can ask now. It's open to you all.